Hi, in this video I want to talk about the Brachiopods Study Task. By now you should have had a go at completing the questions on the worksheet that accompanies this video. If you haven't, now's the time to press pause and have a go at those questions. If you have got a set of answers, let's talk them through. Okay, let's go. The first question is all about identifying these fossils. One of the best ways to tell brachiopods apart from the only other group you're going to confuse them with, which is the bivalves, is their symmetry. So on specimen X here, we can see that we've got what we call equivalve symmetry. There's a line of symmetry between the two shells. So the two shells are symmetrical. In figure Y, the line of symmetry is what we call equilateral. It runs down the middle of a shell so that the two sides of the shell are symmetrical. Now that means that fossil group X is a bivalve, fossil group Y is a brachiopod. Now it's worth emphasizing that this is a general rule. It doesn't always apply. There are exceptions. There are, for example, quite a few bivalves that don't display equivalve symmetry. Oysters, for example. The two shells in an oyster are not symmetrical. There are brachiopods as well that don't necessarily show that equilateral symmetry. So, as a general rule, it works. And if you're asked about it in an exam, it will be a clear example like these are. We can then start to interpret something from the shape of the shell about how these animals actually lived. You can see that a brachiopod has two sets of muscles. To open its shell, it closes the adductor muscles and opens the diaductors. The hinge on these shells pivots the shell open as well, which is why you have muscles either side of that. We can also tell something about how they lived. The fact that we've got a large concave shell, a small convex shell, shows us that these things probably sat in one place rather than swam around. Even more obviously, these fixed spines are clearly not something an animal that moved around would have had carried with it. Those fixed spines are clearly there to hold it in place. Probably fixed in the mud in the bottom of the sea, perhaps partly even buried in that mud, with those spines anchoring it in place. If we look at the distribution of modern living brachiopods, it shows us really what controls their distribution. If we start by just describing what we see though, there's lots of different ways of picking up these marks. Any two of these will get you credit for these marks. The fact we find them in all climatic zones, from polar through temperate down to tropical. Perhaps we don't find them at the extreme poles, but they're there in northern latitudes. We do find more of them in the northern hemisphere. That could be down to the greater continental landmass and therefore the shallow seas that we find around them in the northern hemisphere, but it's hard to say. But certainly there's a greater diversity of these things north of the equator than there is south. We see the greatest abundance in temperate latitudes, 30 to 40 degrees north and south of the equator is where we find the largest diversity of these things. The fewest of them, the lowest diversity, is going to be in polar latitudes. If you use numbers, you have a scale there that you could use to help your answer. That will get you credit. It's about the easiest way to be honest, to pick up marks in a geology exam. Quote any numbers in a graph. You will get credited for it. It will help you just really nail an answer. If we then think about what's actually controlling this distribution, we've got a list of 4 possible factors here. Depth, salinity and temperature of the water, and also the type of material that the seabed is made of. Now, when we look at a distribution like this, that's clearly influenced by latitude, temperature has got to be the key determining factor, the key influence. This, you'll notice, has an R after it. That means it's a reserved mark. In examining circles, that means that to get full marks for this question, you have to have that particular answer. If you give all the explanation without giving that specific answer, you won't get full marks. Notice how the question does tell you what you need to be doing. It's telling you to suggest one of those factors. Therefore, you need to address that issue, that question. For an explanation then, that regular repeating pattern, if we look at from 30 degrees north and 30 degrees south, we see exactly the same pattern. That's got to be related to temperature. The fact it correlates well then with the distribution of climatic zones. Temperature must be a key factor. Particularly then when we look at some of the other factors that you're offered from this menu of choices, they're all local effects. You're not going to see a global pattern of distribution as we see on this graph. And for salinity, well, salinity is, again, a very localized feature. Normal salinity, where brachiopods live, is everywhere. So, the last question asks you to describe the evolutionary history. Now, you're not expected to know this off by heart. You're not going to be asked to recite this information. This is all about interpreting the data. And with a describe question, I think it's fairly straightforward. So we can say these animals appeared in the Cambrian. It's part of the Cambrian explosion. They diversified very rapidly during the Ordovician. But then for the rest of the Paleozoic, up to the end of the Permian, well, for brachiopods, it was about the middle of the Permian, they were in stasis. There was evolutionary stability. Now, I'm sure there were species of brachiopods becoming extinct, but the rate of that extinction must have been about the same as the rate of evolution of new species, because the overall numbers of species of these organisms stayed fairly stable. From the middle of the Permian through into the middle of the Triassic, there was a significant reduction in numbers. Clearly some large extinctions going on. This did coincide, of course, with the biggest extinction the Earth has ever seen at the end of the Permian. There was a small blip, a bit of an increase in diversity during the Jurassic. But following that, there's been a decrease in the diversity of brachiopods. They still exist today, but in significantly lower diversity than we've seen before in geological time. Particularly the Paleozoic era was really the time of the brachiopods. So, to conclude, we can tell a lot about how these animals lived and their evolutionary history from the fossils that we find. They are quite common fossils from particularly Paleozoic sediments. But when we compare them to other groups like the bivalves and in particular the trilobites, and we look at the diversity of habitats that they and ecological niches that they occupied, I'm perhaps a little bit biased, and I think there's some really interesting stories to be told about those particular groups. But I think we're going to save that for another lesson. I'll see you then.